Welcome to lecture number 17. We have already seen that the free energy determination for nucleation as well as for finding growth rate, one has to have a very clear idea on free energy composition diagram, and subsequently the common tangent as well as tangent on the composition of the parent phase where from we are starting our transformation. Now, whatever we have considered apart from that solid base transformation, in order to give an indication that how it is helpful to know free energy composition diagram and to find out free energy difference for nucleation, in all the cases we have considered ideal solution. But situation may be different when we will not get ideal solution, rather we would step into a real solution where we will not have this particular concept valid, because this particular concept is valid for ideal solution. So, if we get into the real system and then subsequent phase diagram, in order to understand that what are the phases that are possible at a particular temperature if we operate the phase transformation at a constant pressure, then we will be requiring the knowledge of phase diagram. And in case of real system where ΔHmix is not equal to 0 in most of the cases, and that time the interrelation between ΔHmix with entropy of mixing would get us the proper knowledge of phase diagram and the variation of phase diagram with temperature. So, let us get into the ΔHmix part, and we will try to find an expression for ΔHmix which will enable us to get phase diagram in case of real system, and subsequently we would also get to know what will be our free energy difference for nucleation of second phase. So, if we try to find out ΔHmix, we have to take help from quasi-chemical approach. Quasi-chemical model. So, this will enable ΔHmix quantification. So, when we start with this quasi-chemical model, it is based on some basic assumptions. So, assumptions are, one is we will only consider the chemical bond energy. Now, whenever we have any solution, whether it is a solid solution, solid alloy or in a liquid alloy, there will be interactions between the atoms. For example, if we consider A and B binary system, then there could be formation of AA bond, BB bond or AB bond. So, all three bonds can form in a solution, and each bond has got its own energy associated with it. We call it as EAA, EBB and EAB. So, this is bond energy and these are bonds. And every system has got its own structure. Let us say if we consider solid alloy formation, then even if it is AB type of solution, there could be several possibilities. Now, let us consider one particular crystal. If we consider a simple BCC crystal, so that means at the center there will be an atom, then there will be bond formation with that atom with the surrounding atoms, and there will be side by another unit cell that could be there on its side. So, there will be side by another unit cell. Now, there will be also the similar crystal structure will maintain. Now, question is, when I consider this particular situation, we say that the bond formation between two atoms would always be there, and this bond will always consider the chemical bond energy. And when we consider chemical bond energy as per classical situation, this is r distance. If one atom is taken from infinite distance to another atom, then I will get attraction force. This will be my attraction force, which is F A. This is force part, and then as the atoms are close together, very close together, then the outer electrons will start interacting, and then there will be repulsive forces also. So, the repulsive force would act like this. So, this is F R, and accordingly its potential energy would vary. So, if I consider potential energy, then the potential energy will be varying like this, and then this is the minimum potential energy, and this is my, if I draw it, this is center of one atom, the center of this is center of another atom. So, this is one atom, and then if I try to draw with a red color, this is another. So, this is the R1, the radius of one atom, and this is the radius of another. So, the bond length is R1 plus R2 is equal to bond length, and bond energy is this one. This is the bond energy. So, this is the bond energy. So, this energy we will consider for our calculation. Similarly, the second assumption is, whenever we consider the bond formation between two atoms, then we could see that for BCC we have a coordination number. And this coordination number we call it Z. In case of BCC it is 8, in case of FCC it is 12. It means that the nearest neighbor atoms and that time the bonds will be only between the nearest neighbor atoms. The interaction between atoms which are not nearest neighbor are not considered in this particular model. So, that means there will be another atom at the body centered, in this case, which is the body centered cubic. So, between these two atoms the interactions would definitely be there, but we will not consider in our particular model construction. So, bonds between nearest neighbor are considered only. And interaction between atoms which are far away, not nearest neighbor, are not considered. The third assumption, apart from bond energy and nearest neighbor bonds, no other interactions are considered. No other interactions. There could be Coulombic interactions, there could be valence bond interaction, all sort of things will not be considered. So, no other interaction are considered. Now, there could be another, there is one more assumption which is very important assumption. Whenever we have, let us say, a lattice of a particular pure atom, let us say BCC, this is all A atom, let us say, all the corner and body center positions are occupied by A atoms. Now, if we consider a replacement of one corner A atom with a bigger B atom, this is my B atom which is much bigger than A atom, then there would be volume dilation in the unit cell, and that volume dilation would introduce strain, and whenever there is a strain there would be also associated with the strain energy. But in our model, which is quasi-chemical model, we will not consider the strain energy part. The strain energy part is ignored, and this also is associated with one particular concept, the concept called that ΔHmix, that means volume before and after solution formation from pure condition, pure A and pure B, and then mixing and forming an alloy. We consider that molar volume would change as per the rule of mixtures. That means molar volume of pure A and pure B would be just added up as per the molar fractions of A and B. So, effectively we do not get any change in volume. So, this is considered as 0. So, which is almost corroborating each other. That means, if there is no volume change, we would not get any volume dilation, and effectively we are not getting any strain energy part. And there is one more assumption we will consider, which is A and B, those are two elements, they have same crystal structure. This would help us to derive the expression for ΔHmix. On these 5 assumptions, we are going to derive the expression for ΔHmix. Now, some of those considerations, important considerations while deriving ΔHmix are, one is, let us say AA bond and BB bond, if we consider, and let us say one AA bond is breaking and one BB bond is breaking, actually we are getting 2 AB bonds. So, one AA bond plus one BB bond is leading to 2 AB bond. Now, if we consider energy wise, so one EAA bond plus one EBB bond actually leading to 2 AB. Here remember, these are not equal, these are equivalent. So, equivalent bonds. So, 1 AB, 2 AB bonds are forming from 1 AA bond and 1 BB bond, and that is what energy wise 2 AB bond is equivalent to 2 EAB, the bond energy, total bond energy after formation of AB bond, which are coming from 1 bond of AA and 1 bond of BB, and that is what this situation is arriving at. So, I can consider that EAB would be having some relation with EAA plus EBB by 2, because these are equivalent. I am saying equivalent, may not be same, because I am getting 2 AB bonds from 1 bond each of AA and BB. Now, there could be situation like EAB could be equal to EAA plus EBB by 2. And if that situation arises, then we have initially complete A, pure A and pure B, and that means pure AA bond and pure BB bond. So, the total bond energy before mixing would be simply total bond energy before mixing would be equal to PA. P is basically nothing but the number of AA bond into EAA plus PBB into EBB, and PAA and PBB total number of AA bond, and similarly this is total number of BB bond, and after mixing I get AB bond equivalent to, let us say, PAB bonds. This is the total number of bonds equivalent to, according to this particular format, AB into AB. And that time we are considering that the entire AA and BB bonds are breaking down and forming complete AB bonds. So there is no trace of AA or BB bonds in the final solution. That time, if this particular concept exists, then I could see that the energy before mixing and after mixing, there is no change in energy. So I will be able to mix A and B completely, and that too randomly. So it would yield a random solution. Now if I see another aspect, which is EAB less than EAA plus EBB by 2, that means after mixing I could see that the system energy would go down. So that means if a system energy goes down because EAB is less than this particular value, so AB bond formation would be preferred. Now this could be a small negative or this could be large negative. That means this value is small negative or large negative compared to this particular added value. I would get two different situations. If it is smaller negative, that case I would get short range order, and if it is largely negative, I would get compound. Now on the other hand side, if AB greater than EAA plus EBB by 2, then if I break this AA and BB bonds and form AB bonds, actually I am increasing the system energy, which will not be preferred by the system. So that case I would end up getting two more situations. One is if this is slightly greater than this particular added value or highly greater than this particular added value, then I would get two situations. In one case I would always like to have a small cluster of AA or BB region, and if it is largely positive compared to this value, largely greater than this particular value, so that case we would get AA rich side and BB rich side. We call it phase separation. Phase separation. So now we could see that this particular value, this particular parameter, if we consider as small e, is very important, very crucial. If it is less than 0, if it is equal to 0 or greater than 0, I would get these many situations. If it is less than 0, I would get short range order or compound formation. If it is equal, random solution. If it is greater than 0, I would get clustering of AA and BB regions or phase separation, A rich side and B rich side. So we would try to relate this E with coordination number, which is Z, as well as composition of A and B, and this composition of A and B means XA and XB. So, in our next lecture we will try to relate this energy difference with composition of A and B in that alloy or the solution and coordination number, and then we will see that how ΔHmix varies with the composition change. With the composition change. Let us stop here. We will continue in our next lecture, where we will address this and this. Thanks.